So welcome back to our AP Chemistry notes. We're finishing up our last topic of our last topic. We're going to talk about titration curves, and we're going to see the effect of buffers in those as well. And for us in our year, this is it. So this hopefully is the last video of the new material, and after we are finished with this and do some labs and a test, we are going to be ready for review. Which the good news there is that gives us a little over 3 weeks, maybe possibly up to 4 weeks for review, and you probably will need it, so it's a good thing we have it. But we definitely need to talk about titration curves. It's a big deal on the test, and they're easy points if you know what's going on. So when we do titration curves, things that you want to be sure you notice. There is the equivalence point. Now the equivalence point, please listen and catch the vocabulary and memorize. Equivalence point is where the amount of acid and base are equal. In other words, the amount of hydrogen ion and the amount of hydroxide ion have been equaled. There is a difference between the equivalence point and the end point. The end point is when your indicator changes color. Your end point does not necessarily have to coincide with the equivalence point, which is why it's so very important to pick your indicator carefully, because you want it to have the end point be equal to the equivalence point. If my equivalence point I'm expecting to be 4, I don't want phenolphthalein, which has an end point at 8. I'm going to be past my equivalence point before I even reach a color change. So you want your end point, the color change time of your indicator, to be close to the equivalence point. How do you do that? You double check that the pKa of the indicator is very similar to the pH of your equivalence point. So you calculate or guess what you think the equivalence point is going to be. You should be able to make at least an educated guess. And then you find an indicator with a pKa extremely close to that pH. So pKa very, very close to pH is what you'd want to go with. And then we have the half equivalence point. The half equivalence point is a point at which, as I said last time, you've added half the volume of your titrant to get to the equivalence point. Well, this holds a magical spot for us in a titration curve. At the half equivalence point, the pH of that half equivalence point is equal to the pKa, which means if you then undo the negative log, you can totally calculate the Ka of your acid. So it's a way to actually find the Ka of an acid right off your curve without even needing to look it up. So you could be in lab with a totally unknown acid, and once you've done your titration with your known base, you can find the half equivalence point, and then boom, with a little bit of math, undoing the negative log, you can find the Ka for that unknown acid, which is probably one of the ways they use to find all those numbers that we have in the back of textbooks for Kas and such. Okay, so those are major important points on our graphs. Now let's look at some graphs and analyze them. This is a graph for a strong acid, strong base. It should look this way. Now there's two versions. So which is which? Well, no, check this out. If I'm starting way down here at 1, I'm starting with strong acid, which means strong acid is in my flask, and I'm dropping in, drop the strong base. How do I know it's a strong base? Because look at where it ends. It ends about 13, strong base region. Okay, so this is the opposite. I'm starting in the flask with a strong base because it's starting at about 13, and I'm ending with a strong acid. I'm dropping in from my burette a strong acid because it ends at a very, very low pH. For a strong acid, strong base situation, we expect the equivalence point to be very, very close to 7. Okay, it doesn't have to be, as we've proved earlier, but it should be very, very close to 7. So where should our endpoint change? Where should our indicator change color? Hopefully around 7. Where's the half equivalence point? Okay, well, check this out. It's by volume. So half of 25 is 12.5. It's like right there. And half of that is going to be like right there. So what's magical about these? Well, I can read the pH right off the side once I know those points. And here at the half equivalence points, the pH equals the pKa. So say here my pH is 1.5. Then I know that that equals the pKa, so Ka would be 10 to the negative 1.5. And you just plug it in your calculator, and there's your Ka of your unknown acid. And it's like a magical point, because now we know the Ka of our unknown acid. Pretty cool stuff, actually. Okay, so that's strong acid, strong base. Whether I start with a strong acid and drop in my strong base and end with strong base, or start with a strong base and with strong acid, that's what we expect there. Okay, here's a strong acid, strong base curve with a buffer. What do you notice as the difference? Okay, well, I start strong, I start low, so it is a fairly strong acid, and I end high, so it's a fairly strong base. Okay, so it looks like my base is a little stronger than my acid because I'm not exactly ending at a pH of 7. But here's the big deal. Check out this region where it seems to like really get a shallow curve for a while. Let me go back. There we go. Notice how that's missing from here. It's a nice smooth curve upwards, always getting steeper, 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 steeper. And then here suddenly it goes steeper, steeper, shallower, shallower, shallow, 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 steeper, steeper, steeper. That is the effect of a buffer. A buffer means it's going to take longer to change pH, which means, because remember that's the kind of like what a buffer does, is it resists change in pH, which means it's going to flatline, it's going to stay close to the same pH for a long while. It's going to just literally like extend and shallow one end of our curve. That's what we would call the buffer region. This is the buffer region, the region during which the pH does not change much. It is rather subjective where to draw that, but it is not hard to see that, oh yeah, that would have a buffer, because otherwise it would be looking like that. So it really does extend the whole graph over to the side. Key indication I have a buffer. Okay, let's talk about weak acid, weak base. First off, how do I know that? Weak range to start with, weak range to end with. I'm obviously starting with the acid in my flask, and I've got the base in my burette, and I'm dropping it in, drop, 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 drop. Now, with weak acid, weak base, I'm still ending about 7, and it would really truly depend on what acid and base I'm talking about. But since I'm talking about ammonium hydroxide and acetic acid, their Ka's match. So I'm going to end exactly at 7. If my base was a little stronger, this would be a little higher. If my acid was a little stronger, this would be a little lower. Those are just the little details you can get right off the graph. So those are good things to know. Half equivalence point. Well, it looks like there's 25, so I go to like 10, so 12.5. There's my half equivalence point. And it looks like I have about a pH of 5. So I could then find with a pH of 5, that my pKa must equal 5, and therefore I can find my Ka. Check this out. There seems to be a little bit of a buffer region there. That's not necessarily unusual, because remember, anytime we have the rice table and we have we could be having a salt being made, and we could have a side reaction going on. It's not, if I have not set up to be a buffer in the first place, it's not going to be a large region, but it could totally be there. Okay, now let's talk about a diprotic acid, and this is a strong acid, strong base. Okay, starts strong, ends strong. And this is a diprotic acid, meaning it can be an acid twice. And notice what I see. I see 1, 2 equivalence points. Okay, well that kind of makes sense. But also notice what I have. I have a half equivalence point for the first Ka, and I have, and we restart counting here. That's what I want you to see. It's not like half of the total now. It's restarting here after the first equivalence point. I have a half equivalence point for the second Ka. So I could totally, with these two half equivalence points, calculate both Ka1 and Ka2. But not surprising for a diprotic acid, we get 2 jumps. Okay. We also get kind of a flatlining going on, maybe have a buffer thing going on. You would have to examine the particular situation, or if they're like, where is the buffer region? And you're like, okay, well, if I'm going to circle it, there has to be one. That's what you circle. Here's a triprotic acid. Okay, again, I start strong and I end strong, so triprotic acid with a strong triprotic acid with a strong base, and I get 3 equivalence points. I get 3 jumps in pH, and that also means I have 3 half equivalence points. And again, that starts over between each equivalence points. So now I could find, Ka1, Ka2, and Ka3 right off my graph. Do you see the power that comes from a titration curve? There's lots of great data you can get and lots of good calculations for information about unknown acids and bases that you can get right off the graph. So these are used a lot on the AP test. A lot. Be able to draw them, be able to analyze them. Okay, now let's talk about the 3 ionization equations for H3PO4. Okay, so H3PO4 is going to ionize. First time it ionizes, you know what, I'm not even going to pretend I know if it's one way or not. We're not going to go there for the moment. You look it up and you tell me, but it's one at a time. Okay, and then I start with the leftovers of the first one, and I get the second one. Wow, just 1H. PO4, 2 minus, and I start with the leftovers of the second one, and I get the third one. So we would expect H3PO4 to be a triprotic acid, and you're like, well, duh, it has an H3 there. Okay, yes, it does, but check out this curve for that. How many equivalence points do you see? Well, I see a jump here and a jump here, and that's all I see. I see 2 equivalence points. That's very typical of real-life titration curves of real-life di- and triprotic acids. What's this mean? This means that the amount of hydrogen given off in that third reaction is so incredibly tiny, we may not at all even notice it. Now, they have very nicely labeled it for us. Honestly, I wouldn't even know it's there if it weren't for like a calculation. Okay, and with knowing where it is, then we have a half equivalence point, half equivalence point, half equivalence point. But I'm trying to point out, for a diprotic and triprotic acid, it's often the case that we don't see the second and or third equivalence point. We might only see one, and that's just the way it goes sometime in chemistry. Sometimes they're so weak by the time they get to the second and third hydrogen that needs to be given off to have another round as an acid that we won't be able to detect it well with the equipment we use. You would need some super sensitive equipment to notice that there's actually a jump there, because it doesn't even look like there's a jump there. So there's some real life chemistry, just something for you to know. And if they could totally ask that question. The graph below only shows what seems like 2 equivalence points, but it's a triprotic acid. Explain why there's a difference. And you just say, well, the third equivalence point, the Ka, is so incredibly tiny that very little product is ever made, so small that it's very hard to determine with our equipment. Okay, well, that's the quick about titration curves. But they are super useful, super important. So you're going to make some in lab and analyze them, and you're going to see some and have to analyze them and things such as that. So very, if I was to tell you that something would definitely be on the test, I'm going to say definitely somewhere on the test will be a titration curve that either you have to draw some parts to, or you would have to label some parts on, or possibly do calculations from, like find, oh, here's the half equivalence point, let me calculate the Ka, or something to that effect. Okay, you might even just have to say, oh, it was a strong acid mixed with a strong base, or a weak acid mixed with a strong base, or whatever. So good luck on it. It's easy, but be sure you've practiced it well enough that you understand all the parts to it, because it's a very important concept in chemistry. Very, very important. Be sure you practice it well and understand it. Good luck on your practice.